We are Team 6, Cube Satellite Test Systems. My name is Duncan Hacker. I'm the Logistics Manager.
I'm Zach Harrington, and I'm the Financial Manager and Safety Coordinator.
I am Rex Calabrese, and I'm the Test Engineer. I'm Andrew Strauss, and I'm the Manufacturing Engineer.
I'm Cliff Whitty, and I'm the Project Manager.
Our clients are the Vermont Space Grant Consortium and Benchmark Space Systems.
The purpose of this project is to build an attitude and control testbed for Cube satellites. Cube satellites are small research satellites that are easy to build and cheap to send up into orbit. To test these satellites, you need a very low friction testbed that can adequately capture the thrust of such a satellite.
The impact of this project will be that our clients will have this testbed to aid in their research to advance the state-of-the-art of CubeSat propulsion. Our clients' major requirements were that the testbed have low enough friction to simulate a space environment, that it be modular to be able to accommodate a wide variety of test components, and that it have a data acquisition system accurate enough to capture the motion of those low-thrust components.
Early on in the design process, the team decided to use an air bearing, which suspends the rotor on a cushion of air to create a low-friction environment. There are other potential options for this, such as magnetic bearings, but we believe that using an air bearing would be more viable with our skills and experience. While we had decided to use an air bearing, there was still the question of what type of air bearing to use. One option we considered was a spindle air bearing, which allowed rotation about one axis and no other motion. The second was a planar air bearing, which allowed translation in two directions and one axis of rotation, but this design required a mounted air tank to keep external air hoses from affecting testing. The third and final option, which we considered, was a spherical air bearing. This allows for rotation about three axes, but no translation. Here's a model of one of our initial prototypes of the spherical air bearing. We eventually selected the spherical design because it does not require the complexity of a mounted air tank, and while it does not allow translation, it is the only design that captures off-axis rotation.
We decided to buy a commercially available spherical air bearing rather than manufacture one ourselves, since we did not believe we'd be able to make it to meet our specifications with the tools available to us if we manufactured it ourselves. For the mounting system, we decided to use off-the-shelf optical components, which have standardized attachment systems and can be easily assembled and disassembled. This allows the testbed to be easily reconfigured and meets our modularity requirement. The team used SolidWorks and existing 3D models of the optical components we used to virtually assemble the components of the testbed. We also used SolidWorks to design custom adapters to attach components, like the bearing and electronic components, that did not fit the optical component attachment system. We then manufactured these adapters with rapid prototyping methods such as laser cutting and 3D printing.
This tank provides clean, dry, compressed air to the air bearing. After going through a primary regulator and a secondary regulator, the compressed air is reduced to the inlet pressure for the air bearing. The air is then plumbed through the air bearing and allows the top piece of the air bearing, the rotor, to spin freely.
Supporting the testbed is our custom-built stand. On top of the stand, we have our bump stops, which restrict the rotation of the bearing from going past 30 degrees. They're telescopic so that you can increase the angle or decrease the angle. Above the stand is our bearing. Above the bearing is the mounting plate, which holds all of the components as well as the payload. Here are our mass balance tuners, which slide left and right on two axes. Below the satellite, we have another stage for XY positioning. Both of these stages are to balance out the mass of the satellite. Here we have our data acquisition system, which includes a gyroscope and accelerometer.
One of our most critical requirements was that the testbed have low friction. We characterized the friction of the testbed with a specification about how much it slows down over a certain period of time. To test this, we spun the testbed at a known rotation rate and used the data collection system to see how much it slowed down over time. In this clip, you can see a real-time graph of the rotation rate as the testbed spins. The line is nearly flat, meaning the testbed is barely slowing down at all. Our specification target was that the testbed slowed down by no more than 1 degree per second over a period of 10 seconds. When we tested, we found that the testbed slowed down by 0.064 degrees per second over 10 seconds, passing our specification.
Overall, we feel that this project was a success because we met all of our client specifications and because we provided them with a piece of equipment that will allow them to do future testing on Cube satellite propulsion systems.
What's next for this project is the actual testing of our testbed using the Cube satellites and the different propulsion and attitude control systems that our client at Benchmark Space Systems has. Using these systems, they'll be able to get the data that they've been missing and hopefully it will work for them in the further development of their Cube satellite propulsion systems.
We'd like to specially thank Lord Microstrain for their help with the data acquisition equipment, Airgas for their help with designing the airline, Specialty Components for their help designing the airline and selecting an air bearing. We'd also like to thank TJ Heffernan for all of his help in the lab, Deborah Frazier for all of her help with the purchase requests, and Courtney Giles for her help setting up the airline. We would also like to thank Dr. Hitton McDevitt for the opportunity to work on this project.